Hey guys, quick review of section 8.0, which is a review itself. We're going to start off by doing a little bit of factoring, solve each problem by factoring. Um, and then we're going to see if we can graph this thing based on your solutions. So this has four terms. My go-to move is to factor by grouping. The first two terms have a 5x squared in them. When I pull that out, I'm left with an x minus 2. The next two terms have a common positive 9, and when I pull that out, coincidentally, I'm also left with an x minus 2. Those two things need to match in order for this to be successful, and when it does, I have 5x squared plus 9 many x minus 2's. This one is not factorable. In fact, it is also never equal to 0, seeing as x squared itself is at very minimum 0. Then multiplying by 5, it's still at minimum 0. And if I take something which is minimum 0 and add 9, it's going to be at minimum 9, so never 0. But x minus 2 is equal to 0 when x equals 2. So looking at the graph, 1 and 2, I hit this point. It clearly has a y-intercept of negative 18, so something like that. And since it is a positive lead coefficient in a cubic, it starts from the bottom and works its way up somehow. Okay. Not necessarily a very accurate drawing of what it looks like, but it takes into account everything that we care about there. Over here, this one only has 3 terms. It's not strictly speaking quadratic because it starts with an x to the 4th, but it is near quadratic. If I say a equals x squared, some people don't bother with that, then I can write this as a squared minus 5a plus 4 equals 0, and that should be factorable. A minus 4 and a minus 1, and substitute back in x squared minus 4 and x squared minus 1. This, of course, gives us 2 of our favorite patterns, or our favorite pattern twice, I should say. Difference of squares in both cases. I can write this as x plus 2, x minus 2, x plus 1, x minus 1 equals 0. And we can see that my solutions are nice and symmetric, plus or minus 2 and plus or minus 1. So 1, 2, 1, 2. This will have a y-intercept at 4, as we can see. And seen as it is a even exponent and a positive lead coefficient, we're going to start and end kind of up. And we end up with something which looks like that, vaguely. Okay. Moving right along. This guy, we can try that same trick for. We can say that a equals x squared. We could write this as a plus a squared plus 3a plus 4 equals 0. And again, you might be thinking of 4 and negative 1, but that's not going to work this time. In fact, this appears to be unfactorable. I don't think that there is a solution. We can always check the discriminant of that quadratic formula, that whole b squared minus 4ac business. So that would be 9 minus 4 times 1 times 4. And that is less than 0, 9 minus 16. And if it is less than 0, there are no solutions. This is what is called positive definite, which is a fancy way of saying it's definitely positive, and probably looks something along the lines of that. So there is no solution over here. Okay, what might be new are the sum and differences of cubes pattern. If I were to distribute here and distribute here, I would find at the end of the day, after doing all that and reducing, that I end up with a cubed plus b cubed in this case, and a cubed minus b cubed in that case. Basically, what we're saying is that a cubed plus b cubed, if I can start there and end there, then I can start here and end here. And I have a mantra, which is same. I take that same sign, b. And then it's an a squared with a different sign. Different than the positive is the negative. This time I have an AB, unlike in a quadratic where there's a 2AB, and always end with a plus. So my mantra is same, different, plus, and b squared goes there. So applying that same mantra, I've got a minus b with the same sign, a squared plus with a different sign, a b, and always end with a plus b squared. Okay. I can use that to factor these other three. I'm going to pause for a second indeed. Okay, here's that first one done, realizing that what was being cubed here was not just n, but really a 2n. So I thought of this as m being cubed and 2n being cubed. Likewise, over here, I'm going to think of this as 10b being cubed and being subtracted from 1 being cubed. So I can write this as 10b with a same sign, minus 1, then a 100b squared with a different sign, then a 10b times 1, so it's still just a 10b. Always end with a plus, and 1 squared is still just 1. Over here, I'm saying that this is going to be z cubed plus 64 equals 0. And I am going to factor it in the same way. Z with the same sign plus 4, z squared with a different sign, 4z, and always end up with a plus 16. Now, is this center term factorable? Let's take a look at that quadratic formula again in the discriminant. B squared is 16 minus 4 times 16. Well, that's a negative. So for the time being, this is unfactorable, but details as events warrant. This is, however, a chapter on extending the real number line. Same idea over here. I'm going to write it as 81y cubed minus 24 equals 0. And, well, 81 is not a perfect cube. 24 is not a perfect cube. We can't do anything. Oh, wait, spider sense tingling. We can divide everything by 3. And when I do that, I end up with 27. Oh, hey, that's a perfect cubed. Minus 8. Oh, that's a perfect cubed. Equals 0. And give it similar treatment. 3y minus 2. There is a 9y squared with a plus. We have a 6y, and we have a plus 4. Discriminant is 36 minus 4 times 36. I think we are stuck for the time being. Okay. Find the solution set now of this one, which is an inequality. We're going to start it in the same way, x squared plus 3x minus 10, and I'm going to say equals 0. And it's not true that it equals 0. In fact, we're looking for where it's going to be greater than 0. But what I am looking for first is those critical points, the points where the boundaries are. So I'm going to factor this as x plus 5 and x minus 2. And my critical points are negative 5 and positive 2. And there they are, negative 5 and positive 2. And I can just look to see where it is greater than 10. If I plug in something less than negative 5, like, for example, negative 1,000,000, then negative 1,000,000 squared is so huge that it's always going to be greater than 10. And yes, if I plug in something between negative 5 and 2, like 0, then I get 0 is greater than 10, and that does not work. And if I plug in something bigger than 2, like a million, 2 squared is so big that of course it's going to end up bigger than 10. My solution is from negative infinity to -5. I don't include -5 because it's not an or equal to. And from 2 to infinity. I'm going to pause here. Okay, we also know that -5, +2, but this thing should look like a parabola like that. When I say this thing, I'm really talking about y equals that thing. So I shifted this down by 10. We're saying, oh yeah, it's above the axis in those two regions. So it all seems to work out. Another one here where we have 4 terms. What would happen if I pulled out an x squared out of the first 2 terms? I'd have a 3x plus 5. And if I pull out a -9, I'd end up with a 3x plus 5 greater than or equal to 0. I've got x squared minus 9. Oh my goodness. Could that be a difference of squares? And I should say equals 0 here because I'm looking for the critical points. X plus 3, x minus 3, and 3x plus 5. My critical points are plus or minus 3 and a -5/3. Additive opposite of that number divided by that number. So -3, -5/3, and 3. We know 3, -3, -5/3, and +3, not really drawn a scale. We know that it is a positive lead coefficient, should look something like this. So I can predict yes in this region from -3 to -5/3. Don't forget your square brackets because it is or equal to, and anything above 3. So union 3 comma, but a curly bracket at infinity because we're never equal to infinity. If you want to plug in numbers to check, be my guest, of course. We've got yet another example of this. To get a -17, we could do 16 and 1. So I'm writing this as x squared minus 16 and x squared minus 1, ignoring the substitution for the time being. Just doing it like that. X plus 4, x minus 4, x plus 1, x minus 1 equals 0, plus or minus 4, also plus or minus 1, 4, 1, 1, 4, upward facing kind of W looking thing. I guess it's downward facing, you call it an M thing. When it is less than or equal to 0, it seems to be between -4 and -1, and between 1 and +4 is an or equal to, so it contains all of those. Again, feel free to check. If I plug in 0, for example, I end up with a 16, and 16 is not less than 0. Okay. There are some additional problems for you to try here. Please be my guest. Important powers, these are the ones which we expect you to know. So 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, 100. And really, I expect you to know any power of 10. 11 is 121. 12 is 144. We've got a 169. 14 squared, I find particularly important at 196 because it's really close to 200. That tells me that the square root of 2 is about 19.6. Is about 1.4, excuse me. Square root of 2 is about 1.4. 225, and way up to 625. 2 to the third is 8, and really you should know a lot of powers of 2. 2 to the fourth is 16. We've got a 32, and we've got a 64 over there. Why would that look familiar? Because 2 to the 6 is the same thing as 2 squared to the third. Well, 2 squared is 4. 4 to the third, therefore, is 64 as well. There's a 27 and a 125, rounding out those. Anything to the 0 equals 1, which we can prove. And 1 to the anything also equals 1. 10 to the nth is a 10 followed by n minus 1 zeros, or a 1 followed by n zeros. Dot, dot, dot. I think that kind of wraps up where we were expecting to get through here. So we will call that a day. Have a good one.